he's coming.
Test 1, 2, 3. Yes, but it's echoey. Is the echo any better? Good now. Great. I can turn down mine. Leave yours the same. How about now? Does that sound good? All right. Any questions from last time? All right. I don't see any from the class, and I don't see any people talking online. So in rapid fire, this is where we started. We were talking about flat plates and that this boundary layer is created by the difference in velocity between the surface and the fluid. And that difference is initiated by what we call the no-slip condition. The fluid at the surface has the velocity of the surface. And this boundary layer had different characteristics. Whether it was moving in structured organized flow in fluid laminae, known as laminar flow, or if it was characterized by mass vortices, or what we call turbulent. And so there's three classic types of boundary layers: the laminar, the turbulent, and in between the two is a transition. And very often, for example, now we're talking about drag. We will have drag coefficients related to which boundary layer you have at the trailing edge. And when we get into frictional resistance in pipes, we're going to have the same thing. So last time, we basically looked at all these drawings and all these figures of a sphere sitting still, fluid moving by it. And remember, relativistically, the fluid could be sitting still and the sphere could be moving through it. Relativistically, it's the same concept. In that latter case, you would become an observer moving with the sphere, and it would appear then that the sphere is stationary and the fluid moves by it. That's relative motion. And for drag, as well as the boundary layer, we need to be able to define the Reynolds number. The Reynolds number is defined typically as a velocity times the length over kinematic viscosity. The velocity is the relative velocity between the fluid and the object. The kinematic viscosity is the kinematic viscosity of the fluid. And the length parameter is specific to the type of object you're looking at. If it's a sphere, it would be the diameter of the sphere. If it's a truck, it might be the smaller dimension of the cross-sectional area coming at you. So again, this is all review from last time. At very low Reynolds numbers, when we were looking at flow past the sphere, we basically saw that we had all frictional resistance. But as we increase, say, the velocity and therefore the Reynolds number, ultimately what we saw was behind the sphere, there was a zone in which there may have been fluid, but it has no component of flux in the general direction of the free stream. That is, it was trapped in this zone, and that zone we call a wake. And why that wake happens is, as the boundary layer starts at the very leading edge of the object, and as it moves along the object and grows, what's happening is, again, the fluid is transmitting this signal that somewhere down there is a solid surface with a velocity different than the free stream. And that signal is trying to be transmitted through the fluid object as the flow field geometry changes. So for example, as we hit the leading edge, the flow field is curving to match what's happening in the object. And as it goes to the trailing edge, again, now the flow field is expanding. And when we have that contraction and expansion, what we're doing is converting between v squared over 2g and p over gamma. We're making an energy conversion. In the leading edge, we're converting P over gamma to V squared over 2G, which is actually fairly efficient. As we go into the trailing edge, we're now reconverting back. We're going from V squared over to 2G to P over gamma, and that's not as efficient. And so what happens is the flow field geometry is changing faster, expanding faster than this conversion from V squared over 2G to P over gamma can happen. And therefore, the boundary layer strips off of the solid object at a location we call the point of separation and goes off into the fluid as this intense zone of shear. And that's what separates the wake from the rest of the fluid. And once we have that wake, the important aspect is that we have a difference in pressure from the front of the object to the rear of the object. The pressure on the front is greater than the pressure on the back. And so if there was no restoring force, this object would be forced to start moving in the direction of capital U. And therefore, there's some restoring force necessary to hold it in place. And that restoring force is equal and opposite of the drag force. So again, as we keep increasing the Reynolds number, what we see is this wake goes through first laminar characteristics, and then a characteristic where you have mostly turbulence, but you also have a zone of laminar subwake. So you have a transitional wake, if you want to call it. And then once you get high enough, it becomes all turbulent wake. And when that happens, you have a turbulent boundary layer. And that is better at transmitting the signal that there's some solid surface that has a velocity different from the free stream velocity, and the boundary layer reattaches. Because the boundary layer reattached, the size of the wake zone is smaller, and so you have a much smaller drag on the object. Again, this is all what we discussed last time. So in general, what we ended up with last time was we compared to what we were doing before with flat plates to now what we're doing with 2- and 3-dimensional objects. And it's the same drag equation. The distinction that we made before is that before we were talking about drag just due to friction. And now the drag force is both friction and form drag, which form drag is accounting for the difference in pressure from front to back. And depending on the Reynolds number, those two may be similar, one may be much greater than the other. It all depends on where you are with respect to Reynolds number. The area, I think it's on another slide. C sub D is the drag coefficient, and A is the object of the area normal to U. So if we had a sphere, like a golf ball, the area that would go in this drag equation would be the cross-sectional area of the sphere perpendicular to the velocity vector capital U. That's a circle. There are some rare instances when you don't use the area normal to U, and I'll be going over that. But if you recall, last time I gave you a big handout, and that handout had the drag coefficient for a lot of different objects. So 3D objects, when there is a wake, this is the drag equation. It's the momentum form of the drag equation as we were introduced when we were talking about drag on flat plates. How we use this equation is we'll either solve for the left-hand side, we want to know the drag force, or we could use this equation to solve for velocity. Typically, this is known as the settling velocity, and we'll probably be getting into that next lecture. And again, when we're using this equation, we always talk about relative motion. So what we set up initially was the object still and U's moving by it. But you could have the object moving and you could have the fluid moving by it, and it's the relative motion between the two, just as we discussed with forces on vanes and the momentum equation. So these slides, these next two, are from the first day of lecture. And when you're driving down the highway, you might see these spoilers on the back of trucks. What do? Well, they're going to reduce the drag coefficient by reducing the wake. By doing that, the drag, this is the power or the force that the truck can generate. And so if you're consuming a lot of energy and drag force, then ultimately what happens is you're going to have a higher velocity. Oh, sorry, a lower velocity. If you can decrease the drag force, since the drag force is a constant, if you can decrease the drag coefficient in order to have no change in the power that this truck can use to generate, to go down the road, necessarily the velocity would increase as the drag force, the drag coefficient goes down. So that's the whole idea. And you'll also see those spoilers on the cab, and you'll also see them on the side underneath the truck, and they're all to reduce drag coefficient. Likewise, these are not uncommon instances out west with trucks or trains. And so what you have is some object, let's say it's the truck. So you're looking at a cross section and you have the wheels at the bottom. And so you have some free stream velocity and it's causing a drag force. This object has a weight. And what you're looking at is a moment equilibrium. So if this thing is about to tip over, clockwise because of the direction of capital U, it would be rotating about that blue point. And so in this case, right at the point of which it's tipping over, the sum of the moments, I probably should choose a different color now. Sum of the moments about that blue point would be equal to 0 when it's just about to tip over, and that would be the clockwise moments, which would be drag times its moment arm, LD, and it would be offset by the weight times its moment arm. Okay, so the weight, you typically know the weight of these vehicles for trains. It's going to act typically centroidally, but you certainly could have an eccentric load. So you should know all the moment arms. The drag force is a resultant of all the little stresses which are acting uniformly over the side of the truck or the train. So this is a very simple moment equilibrium, but the first thing you have to be able to do is unlock the drag force, 1/2 C sub D A rho V squared. And again, in this case, which we'll probably get to next time, but settling velocity. So the drag force in this case is the weight. And it's being opposed by the drag force. And if you're going at a constant settling velocity, then the system's in equilibrium and these two are equal. And what you would be solving for is the settling velocity in this case, velocity that in this case, the parachutist is reaching the ground. And in the old days, they used to have, the cup-shaped parachutes. But by using a more innovative design, what you do is increase the drag coefficient. And remember, the drag force is equal to the weight. And so the response would be that you decrease the settling velocity in this case. So without the parachute, you're going to the ground at almost 200 miles per hour. And if your parachute doesn't open, you have the rest of your life to figure out how to fix it. So if we're looking at any type of structural considerations, again, we have, for example, the building. And the building's sitting on the ground. And what we're going to do is distribute the stress of the building to the ground. So that's a foundation problem. But now you have the wind blowing on this building, and you have to counteract the horizontal loading of this. That's also a foundation problem because that is going to create a drag force, and the soil is going to give an equal and opposite resistance to that drag force. And at the same time, this drag force is creating a moment about the base, and that's also the soil that has to be able to give you that resistance. And then the last thing is structurally, you need to be able to make sure that the structure in flexure can resist this type of bending moment anywhere along its length. So these are more of the material characteristics. So again, you may not be interested in water resources or fluid mechanics, but in all these other areas of civil engineering or environmental engineering, you can't really escape it. So the drag coefficient. Drag coefficient depends on the Reynolds number. In some instances, for a certain range of Reynolds numbers, as you will see, the drag coefficient is almost uniform, it's constant. The Reynolds number depends on the fluid properties. Remember, the Reynolds number is velocity times some length dimension divided by kinematic viscosity of the fluid. The Reynolds number also depends on that dimension. And again, if you have the cross-sectional area facing capital U, it may not be a nice symmetric cross-section. For example, like a sphere has a circle or a square. It could be something different, and we'll talk about which dimension you select when we talk about some of these different objects. The drag coefficient also depends on shape. The shape is affecting the weight. So you could have a flat plate completely normal to the flow or parallel to the flow, and you get a very, very different weight. And again, the dimensionality of the problem you're looking at. So some problems you can look at as a two-dimensional problem. For example, an infinitely long rod. So sometimes when you're seeing these problems in the textbook or on the FE exam, you can certainly go into what are called the 2D drag coefficients. And I gave you some in the handout for today. Actually, I'll cut out of the PowerPoint and we'll go to that handout. And then some of these are for 3 dimensions or finite sized object in all dimensions. So let's get out of this, and then we're going to open up the drag coefficients. So this is the handout for today. And what you see is on page 1, drag coefficient for a sphere versus cylinder. And again, the important thing is to recognize that's why. Well, it's not letting me write on this, so let's try annotation. There it is, thank you. So in this case, what we're looking at is this region. And in that region, again, with an increase of the Reynolds number, you get this precipitous drop in the drag coefficient. That's what the trucks are trying to do when they add the spoilers. This is what cyclists do. A lot of different ways to try to affect this. The dimpling on the golf balls, the flight rings on the Frisbees, they all are trying to push you to the other side and lower the drag coefficient. Okay, and then continuing. On the second figure on the first page of your handout, again, these are for different objects. And if you look at the very top one, the flat plate, you can see that over the range of Reynolds number they're looking at, from 10 to the 4th to 10 to the 7th, it's basically a constant drag coefficient. How do they calculate the Reynolds number? Obviously, it's the free stream velocity. And you can see D is identified in the figure for the flat plate. So this would be, for example, flat plates that are infinite in length. So if you look at the title, you've got it D in height, but it's basically infinite in length. And this is why I distinguish between two-dimensional objects and three-dimensional objects. On the second page of your handout, what you can see is the drag coefficient for a sphere. And so this, you can see where the smooth sphere is. So here's the smooth sphere. And E is the size of the roughness elements compared to the diameter of the sphere. And so as you go to larger and larger values of roughness, what you can see is where you get this precipitous drop in the drag coefficient is occurring at smaller and smaller Reynolds numbers. So almost an order of magnitude smaller. That translates ultimately, if the drag force is how hard you can hit the golf ball, by lowering the drag coefficient for the same amount of whack, you get a much higher velocity and therefore a further distance. And then continuing on that handout, again, if you look at what we had for the sphere, we have drag coefficients that go from almost 200 down to 0.1. And then if you look at a car, you can see how streamlining cars have decreased the drag coefficient almost threefold. That translates into better gasoline efficiency. Okay, so going back to the PowerPoint presentation. This is the sphere and the cylinder, and I just discussed this handout. So let's start off and start with an example that we'll keep adding to this example. So right now we're going to look at the drag on just the flagpole. So ignore the flag, and we're looking at just the pole. And the question is, if we have a wind speed of 30 miles per hour, the flagpole is 20 feet high with a diameter of 8 inches, what's the drag force on the flagpole? And remember, what's going to happen is the wind speed is acting uniformly over the pole. Even though there is a boundary layer at the Earth's surface, we're going to kind of say that capital U is constant over the entire length. And so what we're going to get is some drag force that acts halfway from the bottom and halfway from the top of the flagpole. And so to calculate the drag force, we use the momentum form of the drag equation, 1/2 C sub D A rho U squared. All right, so the velocity is 30 miles per hour. There's 5,280 foot per mile, and there's 3,600 seconds in an hour. So we can convert 30 miles per hour to 44 foot per second. And remember, when these hurricanes hit, so Iota is slamming onto Nicaragua now, and it has a velocity, wind speed, sustained gusts of 140 miles per hour. The area cross-section, the area is the cross-section that's normal to you, and that is the height of the flagpole times its diameter. Remember, the cross-section of the pole is just a rectangle, and that's what's normal to you. So that's 20 feet times 8 inches divided by 12 inches per foot. So the cross-sectional area for the drag equation is 13.3 square feet. And then I went to the back of your book and I looked up the density of air and I looked up the kinematic viscosity of air, both at 60 degrees Fahrenheit. So I didn't give temperature in the problem. Again, what I always have told you in this course or in the FE, if you're not given temperature, assume room temperature. This is not necessarily room temperature, but it's a line right from the back of your book. When you leave here and you're doing designs, you should know what the temperature.
Race 2012, 15.
Yeah. I probably
He's like, go to Gmail right now.
do what?
So I'm going to go into Zoom and mute everybody because evidently not everybody's muted. And it's not like I don't enjoy your conversations, but here we go. Oh, there we go. And I'm not even going to let you unmute yourselves. Hopefully you can still hear me. All right, so back to the presentation. Okay, so the velocity is 30 miles per hour, and the cross-sectional area we had is 13.3 foot squared. And again, we can look up all the information we need. We're going to need the density for the drag to calculate the drag force, and we need the kinematic viscosity for the Reynolds number. So for C sub D, there are two figures in your book, figure 11.5 and 11.8. And so if we have the Reynolds number, and I know these are hard to see, but these are right from your book. If we have the horizontal axis, we can go up to and find the drag coefficient for some type of a smooth object. Here we have a smooth cylinder. Okay, so again, these are cylinders. That's how we're looking at the flagpole. So the Reynolds number is the velocity, and again, the length parameter is typically the smaller of the parameters. So we have a flagpole that's 20 feet high. However, the radius, the diameter is 8 inches. So that's the diameter that we use in the Reynolds number, smaller of the two. So in this case, we've got 44 feet per second times 8 inches over 12 inches per foot divided by the kinematic viscosity, which I again got from the back of your book. And the Reynolds number is a dimensionless number, and it's 1.86 times 10 to the fifth, 186,000. And now that we know that, for example, if we go to figure 11.8 in your book, and I went to 11.8 because compared to 11.5, 11.5 has a very large range for the horizontal axis, whereas 11.8, it's more narrowed, so you can get a little more accurate on it. So we go in at 1.86 times 10 to the fifth and horizontally over, and what you see is that the drag coefficient is about 1.2. Any questions on that?
Yeah, we do. What can you do to the flagpole to make it withstand more drag, or is it the same for every situation?
Could you see that louder?
Yep. What can you do to the flagpole to make it withstand more drag, or is it the same for every situation with the same parameters?
Okay, so the question was, and everybody can read it because it's written there, what can you do to make the flagpole withstand more drag? Let me go through this first, and then we'll talk about that, because that has everything to do with changing the wind speed, which isn't happening yet. So we'll talk about that. So also on the first page of your handout, this is one of the slides I just went over, we have one curve for spheres and one curve for a smooth cylinder, which we're assuming our flagpole is a smooth cylinder. So we would go in at, again, the horizontal axis, 1.86 times 10 to the fifth, and read about a drag coefficient of about 1.2, pretty consistent. They're not always this consistent. You know, these are research results, and people get, you know, a dissertation or a master's thesis by studying these things in wind tunnels and taking data. So you could always have slightly different results. So if you take a diagram like this, you should always reference it for your designs, so people know where you got the information from. And it's always good to have another source, so you can always check to see if there's a wild difference between the two. When they agree, that's good. When they disagree, now you're going to find a third or a fourth source to figure out which one is the better estimate. So again, we have a drag coefficient of 1.2 for both of these sources. So the question was, what's the drag force on the flagpole? Now that we have everything in the drag equation, we have the drag coefficient, we have the cross-sectional area, we have the density of air, and we have the velocity. We just put everything into the drag equation, and we calculate that the drag force is about 36.7 pounds. So if you were able to hold onto that flagpole, at the center of the flagpole, you would be able to just hold it. If you could hold on by 40 pounds, that flagpole wouldn't move. But if you were holding the flagpole at the very bottom, like the ground does, now you have to look at the moment. You have to resist the moment about that point of where you're trying to stabilize the system. So again, this force, the drag force, acts centrally to the flagpole, since we're assuming that the velocity and therefore the shear stresses are uniform along the length. So this force acts 10 feet from the ground or 10 feet from the top of the flagpole. So the moment about the base would be the drag force itself times, again, half the length of the flagpole, since it operates midway along the flagpole. So that's 36.7 pounds divided by, times 20 feet divided by 2, which is 367 foot-pounds. That's the moment about the base. But wait, what about the drag force on the flag? So let's say we have a flag, we're very patriotic, and we have a flag that's 8 feet in length and 4 foot in width. So it's got 8 feet in this dimension and 4 feet in this dimension. And again, when you are asked the question drag force, you're using the momentum form of the equation. The drag on the flag is 1/2 C sub D on the flag, area of the flag, times the density of air and the free stream velocity. The wind is, again, 30 miles per hour. So wouldn't it be nice if we had some way to figure out the drag coefficient for a flag? Interestingly, on page 5 of your handout, you have the drag coefficients for a flag. So in this case, you will see they define a fluttering flag in this case. It's got a height in this case of capital D, which in our case is 4 feet. And it's got a length in our case, which is 8 feet, which is L. So in this case, the area, notice, this is not the area perpendicular to the wind. This drag coefficient, what people do is they measure everything in this equation but C sub D. So they can measure the free stream. They can put this either in a wind tunnel or they can just go outside and measure all this. They can measure the wind speed, and they would define the cross-sectional area as the area of one side of the flag. So this is a case where you're looking up the drag coefficient for a certain type of object, and you have to use the reference geometry that was used in the development of their drag coefficients. So the area in this case is 8 feet times 4 feet, which is 32 square feet. Their length to height ratio, L over D, is 8 feet over 4 feet, which is 2, which is means we would get a drag coefficient of 0.10. Okay. And again, the question was, what's the drag on the flag? So drag is, again, the momentum form of the equation, 1/2 C sub D rho A U squared, which is 0.12 is the drag coefficient, area is 32 square feet, density of air, and then the velocity of 44 feet per second squared. Gives us a force of 8.8 pounds. And that acts 2 feet from the top. It acts halfway of the height. So the height is 4 feet. So it acts halfway along the center line of the flag in the direction parallel to you. So it acts 2 feet from the top of the pole, or 18 feet from the bottom of the pole, 20 feet minus 2 feet. So what would be the moment of the flag about the base? That would be the drag force on the flag times the moment arm of the flag to the base, which is, again, 8.8 pounds times 18 feet. So even though the force wasn't that great, since it's much farther away from the ground, that's a pretty significant moment when you compare it to the moment of what the pole was itself. And then obviously what you can do is combine both of these. So in this case, the total drag force of both the pole and the flag is simply the sum of those two forces. Likewise, the total moment about the base is the sum of those two moments about the base. So this gets to the question I had earlier, how can you make things stronger? Well, that's kind of the opposite of the way you would look at it. First, you would look at a design condition. So let's say you're a structural engineer. The structural engineers have entire code books on what design conditions you should use, no matter where you are. So for example, let's say you're designing the roof trusses for a building around here. The design depth of snow is 4 feet. And there's a density of the snow that we use. Likewise, if you're designing something for earthquakes around here, there is a design earthquake magnitude that you would design around for this location. That obviously changes as you move out to California. If you're designing structures, for example, a flagpole or any other structure, and you're trying to design against wind, we have designed wind speeds that we use here. You've heard of 100-year flood, 50-year flood, 10-year flood. There's 100-year wind speed, 50-year wind speed, 10-year wind speed. There's 100-year wave height, 50-year wave height. Anything that's probabilistic, anything that's random in nature as far as our loading functions, we can put into a probability distribution and come up with these extremes. And obviously, as you move across the country, if you go from here down to Florida, those ambient design conditions change. So once you know where you are, you've got some design conditions, some design wind speed. Once you know that, one of the first things you can assess is, how do I know the cross-section is strong enough? Well, that's kind of one of the aspects of the question being asked. If you are environmental, you may not have taken a materials engineer, but if you're civil, you did take materials. You obviously have failure stresses which can build up in this cross-section. And so at any location in the cross-section, the flagpole is bending like this. And that's putting this side in compression and this side in tension. Both of those are creating stresses. Some materials, aluminum, steel, might be better able to resist these than something that's not very flexible, concrete. Concrete's really good at compression, but it's horrible in tension. It doesn't really support tension. So again, that's a material characteristic. And what you would be doing is you would select your material, which then has known stress strain characteristics, and you would size the cross-section anywhere along the system to be able to withstand the stresses you have at that location. So way up here, the stresses are much smaller than the stresses down here. And that's why you'll see in many structures, the structural cross-section increase. It's telescopes as you move down the system. So that's one thing you would use this information for. The other is for the foundation. So just by sitting the flagpole on the ground, that weight over the cross-sectional area of the flagpole creates a stress on the ground. If that is greater than the yield stress of the soil, the flagpole will sink into the ground, just like when I wear my high heels at the beach, high heels sink right into the sand. So you have a foundation consideration just due to the weight. For the force resistance, the drag force has to be counteracted by a resistance in the soil. And so the soil is basically pushing back. And how it does that is the area of the flagpole in contact with the soil times, at a minimum, the yield stress of the soil. And then the other thing that the soil has to provide for you is the resistance to this moment. So the question earlier was, how do you make them stronger? Well, the first thing is you find your design condition. What is you and what is the geometry of your structure? And then you can define the drag forces and the stresses, the driving forces, the driving stresses. And with that, you then design each component. So for example, if this is your flagpole and you say, well, I'm going to put it in a hole that's just 2 feet deep, and I'm going to make the hole 1 foot in diameter and just put the flagpole in concrete, and that's what we're going to put it in there. But if the soil can't generate that amount of resistance, then the flagpole just tilts over. And you will see this in a lot of telephone poles. So when they have a telephone pole and they string the wires, especially where the wires take a different direction, that weight is pulling the telephone pole in one direction. And unless they have a cable to an anchor in the ground, you'll slowly see that telephone pole start to yield the soil at the bottom and leave. So you can design everything once you have the driving forces. You can define how much area the cross-section of the flagpole has to have in the soil such that it won't fail either due to the force or either due to the turning moment. Okay, so cycling. If you do ride your bike, people will take bikers, put them into a wind tunnel, and they'll measure the drag force. So they'll just have the bikers sitting there and they'll have the wind blowing this way. And then they'll have a cable which can measure the tension, which is the drag force. And again, knowing the cross-sectional area, knowing the density of the air and the velocity, what they can do is take the drag coefficient, the equation, and calculate the drag coefficient. So that's how they calculate these. And again, this is a table right from your handout. There is no Reynolds number in this table. Is it likely that that's the drag coefficient for all velocities? Probably not, but maybe at the velocities most people are writing at. Is it the same drag coefficient for everybody? Of course not, it's generalized. But when you're racing, if you just look at the posture, just lowering your body onto the handlebars, you can see that the drag coefficient has decreased from 1.1 to 0.88. That's a 20% reduction. It's not good on your back, but if you're comfortable doing that, you can actually do your routes a lot faster, or you can go a lot farther with the same amount of energy. And then in racing, you always see them drafting. And again, what that does is the rider in the back is basically riding in the wake of the first rider. And so that second rider is actually in a zone that's not a capital U. It's in a zone that's actually something less than that. And so here you have a 55% reduction in the drag coefficient, or over riding all by yourself, a 43% reduction. But again, this is significant, and that's why you see the riders always drafting, and it looks like they're about a quarter inch one behind the other. And then all of a sudden the one in front will peel off and go all the way to the back so that they can rest up a little bit. And then you can certainly get streamlined systems and incredibly reduce this drag coefficient. And then we talked about trucking, and in this case, this spoiler at the top is known as fairing. And you'll notice this one has a gap and this one does not. Before, what I showed you was fairing on the back, and then there is fairing that you can actually put underneath. But again, what these do is decrease the drag coefficient, which again, just putting on that spoiler on the front, the fairing on the front, 21%. And if you would just close the gap, which is not easy to do because, you know, when the truck turns, that actually has to go over the top of the trailer so that you're not smashing it. So you can see significant drag reduction. And again, that directly translates to energy efficiency. And those of you talking about sustainability, these are some of the sustainable things you can do. So I need you to bring this handout on drag for next time, because what we want to talk about now is drag on spheres and settling velocity. So just to give you an idea of where we're going to have a sphere and it's going to have a weight W. And in this case, let's say it's an air or water or any fluid. And the fluid is quiescent. It's not moving, it's still. And so what would happen is this particle would reach a settling velocity v sub s. And once you achieve constant settling velocity, what you're doing is developing a drag force that, again, the drag force is equal to the weight of the object. Okay? So that's the real system. And now with relative motion, you become an observer moving with the particle, which in this case, we assume it's spherical. And so this system looks like the sphere is sitting still and the fluid is moving past the sphere at V sub s or U. And so again, what this is doing is creating a drag force, and that drag force is opposing the weight. And so what you'll see is there are basically three equations, which we, and these are all on your handout for next time. These three equations describe this scenario, and from all of them, what we can get is the settling velocity. So how do we use this, for example, for you environmentals or any of you engineers who are doing construction site erosion and sediment control? You have a fluid coming in with sediment. And so let's say it's entering this sedimentation basin. So this is just a big tank of water. And you've got some discharge in, and you've got some cross-sectional area of this tank. And again, this could just be an excavation in the ground, but the horizontal velocity is Q over A. That's an equation you might have heard of called continuity. And what we do is try to size the length and the depth of this basin such that when a certain particle size enters, it's being acted on by the settling velocity. And before the fluid hits the end of the tank, that particle settles out. And so since you know the velocity and you know the length of the tank, the settling time is equal to L over V. That's how long it would take water to move from the left-hand side to the right-hand side. And what you want is the time it takes the particle to go from the surface all the way to the bottom has to be a time that's less than that. And then you'll settle out that particle. So basically, you can identify which size particles you can settle out. Typically, we can get out sands, maybe fine sands. But particles smaller than that will take days to weeks. Clays will take months. And so when we have finer particles, we have other ways of settling. This is just gravity settling in this case. So are there any questions? No? And I'm going to let you out 2 minutes early again. Expect homework, and it will be homework, back on the boundary layer stuff to drag, which I avoided giving you because you were studying for an exam. Okay. All right, that's it.